Yesterday we worked with rates, ratios, and proportions. Today we want to focus more on the side of applications of proportions. Where do we use this? How are they helpful? In the real world type of situations. So copy down your target. There's kind of a couple parts to it today. And then we have a warm-up here. If you want to try it with me, you can. If you want to pause and try it first, then press play, you can do that too. So for the warm-up, an environmental scientist wants to estimate the number of carp in a pond. He captures 100 carp, tags all of them, and then releases them. A week later, after they've mixed up with all the rest of the carp, he captured 85 carp and recorded how many of them actually had tags. His results are shown in the table. Write and solve a proportion to estimate the number of carp in the pond. You can set this up a lot of different ways, but what I like to think about is, what do I want to solve for? I want to solve for the total number of carp, which means I want my proportion to involve a total. I set mine up to say, well, 20 out of the 85 total were tagged, and that should be equal to 100 that are tagged out of the whole pond, and X is the whole pond's amount of fish. So you can cross multiply here and then divide by 20, and you would have 425 carp. You could set it up a lot of different ways, but this is one proportion for this problem, okay? Either way, you should end up with 425. So you have a few definitions here. We've seen these words before. Congruent means that they are the same shape and the same size. They are exactly the same. Whereas similar, they should still be the same shape, but they may be a different size. These two triangles here that I'm showing you are similar triangles. Just a little tidbit, the congruent symbol would be a wave over an equal sign, and the similar symbol is just kind of like the little curvy wave top part of the congruent symbol. Remember, so here's the important thing. Two figures are similar if and only if the ratios of their corresponding sides are proportional and pairs of corresponding angles are congruent. So within these similar triangles, angle A is going to be congruent to angle D. Those two correspond to each other. They have exactly the same measure. Angle C is going to be congruent to angle F. They're corresponding angles, and angles are congruent in similar figures. But the side lengths are not congruent. They should be proportional. So when I look at this picture, AC, this side, corresponds to what side over here? You kind of think about, well, what's the same side on the other triangle? This is like the slanted side over here. That's similar to FD. If we set up a ratio there, 5 to 3, that should equal the ratios of the other sides. Let's do this one. CB corresponds to FE. So we had 5 to 3. That should equal 10 over 6. Is 10/6 equivalent to 5/3? Yeah. If we divide these both by 2, we would get 5/3, so those are equivalent ratios. Same thing on the bottom one then. Just trying to give you some different mental pictures of the corresponding sides. Side AB is going to correspond to side DE. 20 over 12, when you reduce that, should equal 5/3. So that's what I mean by ratios of corresponding sides. They should be proportional to each other. When I reduce them all down, they all reduce to the same ratio. We can use this idea of proportions to solve for missing measures in similar figures then. Take a look at this first example. I have two trapezoids. I have some side lengths, and I have an unknown side length. If I want to solve for x, I would need to set up a proportion. There are lots of ways to solve an equation. Guys, guess what? There are tons of ways to set up the proportion. So your proportion may look different than mine, okay? I always focus on the fact that you should have symmetry, and you want to pair up each corresponding side. So let's talk about AB. AB corresponds to what side on the other figure? AB is like the long base on the trapezoid, so that would be the same as NO on the other trapezoid. So AB should correspond to NO. That means 7 over 5 should be equal to, now make sure when you fill in the second fraction, you pull the top number from the same figure that the top number came from over here. So 7 came from this first figure. Make sure the top came from this first figure over there. I want to find x, so I better use x. What side does x correspond to? It corresponds to this mn, or this 2. Since the ratios of the sides should be proportional, we can cross multiply and solve this proportion to find x. We cross multiply here and have 5x equals 14. Then I could divide by 5. And I would have x is equal to 2.8. Don't forget your units because we are talking about a length here, 2.8 inches. Again, that's one proportion you can set up. You could do a lot of it. Try the next one. Make sure you're comparing similar figures. You can't compare, you can't match up triangle ABC with trapezoid BCDE. You have to be having similar shapes. So here in this picture, think about pulling the picture apart. We actually do have two triangles. ABC is one of the triangles, and then ADE is another. So label the lengths over here that we have. A to B is x, and B to C is 3, and DE is 6. What is the length from A all the way down to D? What's this length here? What could we use to represent that? Well, that whole length is not just 4, and it's not just x, it's x plus 4. Now, maybe you can set up a proportion. Match up the corresponding sides. So if I want to start with x, what does x correspond to? X to x plus 4 is equal to, this came from the small triangle, over here has to come from the small triangle. Keep it matching up. 3 over 6. Go ahead and solve this proportion. Watch out for that quantity there, so we want to do 3 times that whole thing. X equals 4. Don't forget the units here. We're talking about centimeters. So it's going to be 4 centimeters. So that's how proportions can be helpful with similar figures. Another thing that proportions help us with is indirect measurement. Sometimes we can't measure everything in real life. Whereas if you can visualize similar figures or make similar triangles out of something, then you could measure the lengths that you can reach and solve for the ones that you can't. So think about it. Many objects form right angles with the ground, and you can apply what you know about similar triangles and proportions to solve for a length that is not easily measured. In this example, we have a flagpole and it's casting a shadow. Where would your shadow be? On the ground. So here's my flagpole. My shadow's all the way over here on the ground. And if I connect the top of the flagpole to the end of the shadow, I would have a triangle, a right triangle at that. A flagpole casts a shadow that is 75 feet long. So the shadow is 75 feet long. Label that shadow down here on the bottom. At the same time, a 6-foot man casts a shadow that is 9 feet long. So his shadow is 9 feet, and he's a 6-foot man. Let's label this guy right here. You can draw a little picture on your notes. It'll help you visualize it. Same with this, the idea of having a right triangle. We can set up a proportion to solve for the height of the flagpole. This is what we don't know, and we can't really climb up there to measure how tall it is, but we can measure our shadows on the ground, and we can measure our own heights, so we could figure out how tall the flagpole would be. Your proportion, again, could be set up many ways. I'm going to say x corresponds to what on the guy? His height, so it's 6. And then their shadows correspond to each other as well. That's one way to solve it. You can have 9x equals 6 times 5 is 30, carry the 3, 6 times 7 is 42, plus the 3 is 450. Divide by 9 on both sides, and you have x is equal to 50. Don't forget the unit, we're finding the height of the flagpole, so that's in feet. Again, one proportion, guys. You know, another way you could set this up is you could say x over 75 is equal to 6 over 9. This would also work. Take a look. When you cross multiply, you'd end up with the same equation that you had down here. 9 times x and 6 times 75. That's exactly what we had before. So there's lots of ways you can set up your proportion. This is just one. So you'll be doing some indirect measurements with proportions as well. The last thing I want to talk about is the changing of dimensions. If every dimension on a figure is multiplied by the same number, then the result is a similar figure. The multiplier is called a scale factor. One important thing that you do need to write down as a scale factor is always new to old. So if you write it as a fraction, it's always the new figure over the old figure. Make sure you have that on your paper. It's important. So for this example, every dimension of a 2 by 4 inch rectangle is multiplied by 1.5. So this is the one I started with. This is my first image, and it's going to be multiplied by 1.5, every dimension. And I'm going to end up with this second figure, which I labeled B. What is the ratio of the perimeters, and how does it relate to the ratio of the corresponding sides? And then you're going to find the areas of the new figures, and you're going to say how its ratio of the areas relates to the ratio of the sides. So here's what I want you to look at. If I asked you what the scale factor was from A to B, you always have to do new over old. My new is 6, my old is 4. 6 over 4 would be your scale factor, but you can reduce that. So your scale factor is 3/2. You can do it with the other sides too. New over old is 3 over 2. So your scale factor is 3 over 2. Isn't that what this is right here? 1.5? Yeah. So let's find the perimeters of these. Find the perimeter of A, find the perimeter of B, find the area of A, and find the area of B, and fill them in your table here. If you need more time, pause the video, or keep going if you already have them. So the perimeter of A would be 12 inches, the perimeter of B would be 18, the area of A would be 8 inches squared, and the area of B happens to be 18 inches squared as well. It's kind of weird, but it works out that way. All right, so now I want you to set up what is your ratios here. What is the ratio of just the sides? Let's always do the new to the old. So in this case, let's do B over A. For my sides, 6 corresponds to 4, and 3 corresponds to 2. Now let's set up those ratios for your perimeters. What's the ratio of the perimeters of B to A? Well, my perimeter of B was 18. My perimeter of A was 12. Reduce that down, though, and you see that that's actually equal to 3/2. Kind of interesting. Let's look at the areas. When you look at the areas, the area of B is 18. The area of A is 8. Reduce that down. What does that get you? Divide them both by 2, you get 9/4. Do you see a relationship between these ratios of areas and the ratios of the sides? Or the ratio of the perimeter and the ratio of the sides? This is a relationship that exists for all similar figures, and it deals with their scale factor or the ratio of their sides. So write this down. The ratio of the sides is equal to the ratio of the what? What do we find that was equal? The perimeters. So those are always going to be equal. But the areas weren't equal. The ratio of the areas was equal to the ratio of the sides squared. If I take 2/3 and I square it, I would have 2 squared and 3 squared. I'm sorry, not 2/3, 3 halves. Sorry, the ratio of the sides was 3 halves. If I take 3 halves and I square it, don't I get 9/4? And isn't that what I saw right here in this ratio? Yes. So that is the relationship that's always going to exist. The ratio of the perimeters is always going to equal the ratio of the sides, and the ratio of the areas is always going to equal the ratio of the sides squared. So B is an extension. You can try it. Maybe you can make a statement about what the ratio of the volumes is going to equal if you think about that. If you don't know how to find the volume, it's length times width times height. This example, guys, is a little extension. I'll post the key after the video.